Hello everyone, I hope you're doing well. Today I'm going to start chapter 8, discuss flow in pipes, and you will need that for this assignment. The deadline is for next Monday, and I'm trying to finish chapter 8 today and solve some questions next class, but let's see how much it's gonna take to finish it. So first, let's talk that what is a pipe flow. So at first, you have to know that if the flow is in conduit, then doesn't matter what is the cross section area and what is the shape of cross section. It has its name of that is a conduit, and the flow is constant. Okay, but there is two definitions here that you have to know. That first, if that's a circular shape for the cross section, then it's known as pipe flow. But if it's non-circular, then it's a duct flow. That's just a definition, because the pipes, like circular pipes, are very popular, and that's why we use it for most of the in companies, in food companies, for transferring water, for cooling, also in the whole body we have the vessels that all are like pipe flow, and the cross section is almost a circle. So first we have to know that what was the Osborne-Reynolds experiment. So Osborne was doing experiment on Osborne-Reynolds. Reynolds is his last name. He was doing experiment on the pipe flow, and he found out that at first, when the velocity is very slow in the pipe, doesn't matter what is the size of the pipe. At first, means the length of the pipe. It shows that at first it's very smooth, the streamlines, but it shows that by smoke or very small particles, like solid particle or something that can be seen in the fluid. So he found that at first it's very slow and smooth streamlines, but after a velocity, that by increasing the velocity, you find out after a small amount of velocity, it shows that the flow, the streamline is not any smooth anymore. And then after that, it shows that it's highly radical, and it changed so much. It's like transition. It is like turbulent, and it's a chaos there. So it put a name here as laminar flow, and then transient flow, and or transient or transitional period, and finally is a turbulent flow. That's fully turbulent. It's just a start of the noise. Okay, but it just marked the velocity here and found that okay, so after velocity it shows that the transient is started, and after another velocity the fully turbulent flow starts. But by changing the size of velocity, or by changing the type of fluid, we found out that the velocity that is marked for showing the transient is changing, even though that the velocity diameter are changing, or the smoothness of that changed, or the fluid type changed. Everything is going to be moved. So we found out that there is a combination between those, which is Reynolds number. That the Reynolds number, for even though that you have a different pipes with different sizes or different fluids, it all shows that in around a number of the Reynolds number, which is a combination of the fluid type, its density and viscosity, velocity of the flow, and also diameter, so it's the geometric shape of the pipe. These are the only parameters that affect on the laminar to transition period. And it shows that after a number here, which is 2100, it starts the transient period, and after that in this period of 2100 to 4000 you will have a transient but not fully turbulent, but after 4000 for the Reynolds number you will have fully turbulent flow. So we are talking about two types of the flow here, like pipe flow and duct flow. For the pipe flow, absolutely the D, which is the characteristic length, is the diameter of the pipe. Characteristic. Okay, so that's the diameter of the pipe. But if the pipe is non-circular like duct flow, we will find out how we can find it by simple calculation. That what is the characteristic length when the cross section is like a square or rectangle or whatever. So we'll find out that how we can find the D is not any length of it, but we'll find out what is the characteristic length there. But for now, to find out what is the Reynolds number, you have to use rho, velocity, the characteristic length, and mu to find out what is the Reynolds number. And if the Reynolds number is less than the 2100, you can be sure that the flow is laminar, or after 4000 is fully turbulent. And also in the transient you have both laminar and turbulent flow. Here you will have fully turbulent, here and here are the marks for laminar, transient and turbulent. But now let's talk about the entrance and then laminar flow, and we will talk about turbulent later. So first I'm going to show that how the flow profile velocity will change when it's coming to a pipe that is here, that's our pipe, and it's a pipe flow and means that the cross section is circle. Then we'll talk that how the flow changed when it's started from entering to it's not the end. Let's say that is a long pipe. Okay, so at first the flow, when there is no wall there, the flow is uniform, is the free form of the flow that comes in. Okay, so when the flow comes as a uniform, it means that between the layers the derivation of the velocity or y is 0. Why? Because velocity is a vertical line, and if you get the derivation or partial derivative of velocity, component of velocity versus y, then you can find that it's 0, right? When that's 0, then it means that we don't have any viscosity effect between the layers or any shear stress between the layers, right? Because the shear stress was tau is equal to mu minus mu times this derivation, right? It means that it's going to be 0. Or we can write it down that the velocity here, or the flow here, is inviscid. Okay? So a flow means inviscid is always equal to u, and that's a uniform flow. Okay? But after it comes in to the pipe, and we know that we have a boundary condition here, which is no slip boundary condition, right? It has to stick to the wall because wall doesn't move. So here you will have suddenly change to 0 and at the walls, and also you have a uniform, still uniform inside of the in the core part of the flow, right? That it means that is a stick here, and because of sticking to the wall, the next layer is going to be it shows that there's a friction between the layers, but it's moving to the center because the layer on top that is close to the wall going to stop, and then it stops the next layer that is close to it or decrease the velocity of that, and that also is going to stop or decrease the velocity of the next layer after that and the next layer after that. But it took time for the flow to get the effect of the no slip boundary condition to the center of that, right? So that's why. So at first you will have 0 velocity here, but the next layer by itself has the same uniform flow. So you have uniform flow here, but suddenly goes to 0. Okay? In the next step, you will have the next one is 0 still here. The next one going to decrease, but the others stay the same. And the down layer is again stop. Okay? So here these two are decreased. If that would be the book, or if you Google that, you will find out that's much better shows. Here I try to in the note to show that much better than that, but you will see that here is 0. You will have a lower velocity in the next layer, but suddenly change again to uniform flow. Okay, in the next one it means that after a distance here, you will have the 0 velocity at the wall. You will have much lower velocity here, much lower velocity after that, but again the center is still uniform flow, right? Then it shows that the flow is still coming. It's not wholly parabolic, but it's parabolic here, but uniform at the center. Okay, and then after part, or if you get time to that to find out how to match itself with the flow that is inside the pi, is going to be fully parabolic. Okay, so if I just change, if I just show that, okay, it's like, you can say that it's like the warming of water. At first, you warm up the wall, and it's going to transfer the heat to the next layer, and that to next layer, and again to next layer, right? So if I just show that from the boundaries, that the effect of no slip boundary condition is transferred to the next layer. At first it's here, and the next one is coming here, because it's the second layer is now affected by the first layer, which is the wall layer, and then here is going to be more and more to the center, right? From down also you can plot the same thing here. Okay, these are two boundary layers that going to reach each other at the end. Okay, so at first its boundary layer starts here, then grows and grows to reach the center of the pile. That's all boundary layer, and in boundary layer it means that the flow is not inviscid, or you have viscous flow. Okay, so here you have viscous flow, but in the core, that from here and here and here you will still have it, you will have inviscid flow. In the core you have inviscid flow, but in the boundary layer you have viscous effect. Why we have viscous effect? Because the viscous flow means that the layers affect each other, and you have the velocity change with y, right? So we found out that at first it's 0, and then in the next layer it's going to affect the next layer and next layer to the center of the part. That means that you have an entrance, which is entrance region. In the entrance region, till you find out that the boundary layer grows up and reach each other. In the entrance layer, you will have this inviscid core from the entering part, that you have fully inviscid flow, and the core is the whole cross-section area, but it's going to grow or smaller or shrink to 0, and then you have fully viscous flow. That's from here, that entering part, to when the flow is fully parabolic and you have fully viscous flow and boundary layer grows to the center. That would be your entrance region. Okay, why we need to understand what is the entrance region? Because the flow after entrance region keep its parabolic shape as much as it goes forward, right? So it means that after that is fully developed. Fully developed flow means, what is fully developed? Boundary layer. Boundary layer fully developed after the entrance region. Okay, so when the boundary layer fully developed, it means that you have a fully parabolic shape of the profile velocity profile, and then after that the velocity profile is independent of the x. If that's our x, okay, if that's direction of x, after that velocity profile keep its shape without change, is independent of x, only depends to what? R, right? Because the cross section, you will have a cross section area that the velocity at the center is high, but is moving to the, with the R moving to the wall, is going to be 0. So here you have 0, but here you have u max, right? So at the center you have u max, and here you have v0. Okay, that's why it's going to be a function of R. But whatever you find as this cross section area, that could be here, if you again find it out here, because you are after fully developed region, you are in the fully developed region or after entrance region, then nothing going to change. Okay, that's the whole thing that you have to know about the flow that passes. But again, we are talking about the critical Reynolds number, so you still have the same velocity here. Okay, if you have a velocity profile that comes in and the Reynolds number is around or less than the critical length, so your Reynolds number here is less than the critical Reynolds number, then the flow is laminar, and you can say that it's fully developed like this. But if you have a Reynolds number very high, then nothing going to be like this. The entrance region would be totally different, and also the flow doesn't keep its shape because it's going to have chaos there. Okay, so we are talking about laminar flow, and in the laminar flow, that most of the flows, especially in the whole body for vessels, and also in most of the things that you have in the food companies for washing, or most of the things, you will see that your flow is laminar because the velocity and Reynolds number is not much high, and your flow is in the laminar region. And if it's laminar region, you have to know that after the entrance region, you will have a fully developed region that the flow velocity profile doesn't change. Okay, and its main part in your analysis that, okay, we are in the fully developed, then we can say that over x nothing going to change. Okay, and based on that you will assume that the velocity profile doesn't change, so it's going to be a steady, because here you don't have steady, right? It's a standard in trans region. It takes time for the flow to move from here and reach here, right? So it's over time it moves, and based on the velocity you will have it's not a steady. But after that, the flow is steady. Okay, so how we can find that, what is the entrance region and how long it took, not in time, also can find the time, but how much length it took for the flow to find out that it's a parabolic shape, right? To get to the parabolic shape and pass the entrance region. So we'll put that, what is the entrance region show with LE, right? We'll show that it's going to be LE. And if that's LE, we can find out with the combination of that with the Reynolds number. Okay, so that's why again laminar flow and turbulent flow are totally different. The equation for that is also totally different. So you have also in trans region that you have a transitional period, because you are moving from a uniform flow MVC to a fully chaos. Then it's going to have an entrance region that changes like this one. And then after that you have fully chaos or fully turbulent flow. Okay, so also in both of them you can find what is the entrance region, and the entrance region for these two can be found out by two equations, and both of them are related to Reynolds number. Okay, so it only depends that the question asks you that can you find the entrance region that the length of entrance region, that the flow is changing the velocity profile, especially for laminar flow is only asked, but in the turbulent also needed sometimes. But if it asks you that what is the laminar, if that's the flow is laminar flow, what would be the length that the flow needs inside the pipe to fully develop? Okay, that's the whole thing that may ask you for that. But again, it's until the Reynolds number 4000, which is the critical Reynolds number for moving from transient to fully turbulent flow. Okay, that's for now. Is knowing that how the velocity profile changes over the pipe in the laminar, and also for the turbulent you will have chaos. Okay, so that's for now. But what we are going to do here, we are going to find out what is the velocity profile, what would be the forces to find the top, because you know that after fully developed flow, fully developed laminar flow, that we are going to talk right after that. We are not talking about entrance, because entrance is not steady and it's going to only take a length of the pipe. Okay, so for example, you have a pump, the flow is at rest, then pump going to pump the flow inside the pipe. Okay, if you assume that you have a cooling system in a company, then only at the start of the pipe you will have that entrance region, but after that you will have fully laminar to develop laminar flow. So that's why you only took care of the part that's going to stay for whole the pipe system, except for 1% or maybe half of the percent of the length of the pipe. Okay, that's why we are talking about the fully developed laminar flow more than the rest of it. Okay, so for that, let's say that what would be the flow. As at first we talked that is going to be steady, right? In the entrance region, you may not have the steady state condition, but after fully developed, it's going to be steady. So it means that all the components of velocity, the partial time partial derivative is going to be 0, right? And also it's one-dimensional. What does it mean one-dimensional? It means that only depends to r. What? Because the flow is coming to the pipe and is not changing with x, so components of velocity is not function of t, is going to be 0, it's not function of t, and also this v is not function of x. Okay, so both of them has to be set as a assumption here. That's a true assumption that the flow is not, velocity is not function of t and not function of x. And also for y it has to be r, and also for theta. So v is not function of r, t, time, is not function of x, and also if that's your pipe, it's going to change by r, but it's not changing over theta. It means theta means that if that's your cross-section area and that's your r, then theta would be here. So whatever your velocity that you have for r equal to r, for example, that would be here, then it's going to be for whole the circle is going to be the same. That's why we are saying that this v velocity is not function of theta as well. Okay, so it's not function of theta, it's not function of t and x. And also when the flow is one-dimensional, it means that you have only one component of velocity. Which component? Is not going to be v. If that's your x, the flow is not moving upward, is not moving to y, and if that's your y in z and y, they're not moving these two, so both of them is going to be 0, right? So velocity is only u component, right? Velocity is u in I direction. And what's your job? To find an equation for this u, because u is only a function of r. That's the whole job that you are going to do. You are going to find out if the flow is one-dimensional, steady, and based on this assumption, so I know that the u is going to be function of r. What is the answer for that? Okay, let's find out. To find out that, let's do the force balance here to relate the velocity at first to tau, because tau is part of the thing that velocity comes inside of that, and you have also additional velocities here, forces here. One is the pressure at the start, at the end, right? Because the pressure difference is here, that should be there. Delta P should be here because you have pressure difference, and because of that pressure difference, the flow moves over the pipe, right? If the pressure is nothing at both of them, so velocity pressure at the start and at the end of a pipe is the same, then the flow doesn't move because there is not any forward force for that to move inside the pipe. So we know that we have to assume, and we have to know that the pressure is at the start is different with the end, and also we know that the pressure at the start should be higher because every time the flow passes from high pressure to low pressure, and also like a heat from high temperature to low temperature, that heat moves. You can assume, you can physically understand that, okay, that's a higher temperature, so from higher temperature to lower temperature you will have the flux of heat. Here you have a flux of flow from high pressure to low pressure. So that's why we put P1 here as an entrance pressure, but at the end we assume that, okay, if the difference pressure is delta P, we don't put the P2 here, we put the P1 minus delta P here, okay? And also you know that this is a viscous flow because we are in the fully developed flow, and in fully developed flow you have what? You have parabolic shape. You have parabolic shape, and then you have shear stress at the wall and around of that, okay, inside of that. So okay, if I assume that this is my control volume, then in the forces would be, one is P1 AC1. P1 AC1 means the cross section area here, okay? And you have P2 AC2, which is area here, okay? That's the velocity, and the X is also in this direction. What are these? The sigma of X, okay? So sigma of X is one force in this way, one force in the negative direction, and also tau AS, which is the surrounding area of the cylinder, is going to be AS, it shows by AS, times tau, which is the pressure, the stress, shear stress, is going to give you the whole forces that affect on this force balance for this fluid element could be part of the pipe, but is equal to the whole momentum that comes in and goes out, right? So here you will have N in this direction and N out. So velocity comes in here and velocity goes out here, okay? So by itself, m dot 1 it has to be equal to m dot 2 because of the conservation of mass. But before that, we know that it has to be m dot times velocity and the angle between the velocity and n. So v1 dot n is going to be negative here, but here going to be positive. That's why we have plus v2 m dot 2 and minus v1 m dot 1, okay? But before going start and put the pi r1 squared, pi rl, and the answer for AC1, AC2, and the other things here, let's apply conservation of mass. If we apply conservation of mass, then we find out that on control surface area, rho v dot n dA has to be 0. Why? Because the steady, I get rid of the steady state term, and dm, or total derivative of mass, in a system should be 0, right? So then it means that rho 1 AC1 and V1 plus, that's going to be negative because V dot n in that term is in the entrance is going to be negative, plus rho 2 AC2 V2 is going to 0, okay? Rho 2 AC2 V2 is going to be 0. This summation is going to be 0. Then it means that m dot 1, that's going to be m dot 1, and that's m dot 2. right? So at first m dot 1 is equal to m dot 2. What else? Or else we have to know that AC, the cross-section area, is a pipe with that the cross-section area is constant. Okay? Then AC1 also is equal to AC2. And since we assume that this is the flow in laminar direction, laminar flow, and if the flow is incompressible, that most of the time is, we are going to make it simple and simple. So rho is a constant, then we can say that V1 and V2 are equal, right? M dot M2 equal, so rho AC1, rho 1 V1 is equal to, should be, because of conservation of mass, it has to be equal rho 2 AC2 V2. Since we assume that it's incompressible, we can get rid of these two, and AC1, AC2 are equal. So V1 is equal to V2, right? But again, that's the velocity profile, right? When you have a velocity profile, it means that for finding the m dot, you cannot apply rho AC or V1 or V2 or whatever as only velocity, because velocity locally changes in whole the cross-section area. So whatever we are talking about here is the bar one. It means that the average velocity of that, okay? But for now, we know that the velocity is equal, even though we know that the velocity profile is the same. So absolutely, when the velocity profile is the same from here to here, then we can say that the average velocity, which is the Q over A, that's the average velocity, and we talked about before that how we can find out what is the average velocity. It's the total volume flow rate over the area, okay, when the velocity is locally changes. So again, velocity average are absolutely the same because the Q is the same and also area is the same. So velocity profile is also constant over the flow because we are in the fully developed laminar flow. Okay, perfect. So we know that again, these two terms, V1, V2 are the same, m.1, m.2 are the same. So we can say that we can get rid of these two terms, right? If we get rid of these two, what we will have left here? We can write down that P1 minus P2, which is from here to here, and AC1, AC2 are the same, so we can assume that is AC only here, P1 minus P2 times AC, and bring the tau AS the other side and make it positive, and we get rid of these two terms because we found out because of conservation of mass that these two are the same. So we get rid of these two, and we found that this is the force balance now using the conservation of momentum, and we can replace AC with pi r squared 1 with pi r squared, and with for the AS with 2 pi r L that we wrote it here. What was that? Okay, so what we can do here, we are going to find what is the delta P. So first, this is going to be your delta P, right? Because P1 minus P2 is going to be delta P, and P1 is higher than P2, and we can write it down here that here we have a delta P times pi r squared, which is AC, is equal to tau 2 pi r L, which is surrounding area. Okay, if you get rid of the pi term, then what will we have finally? We will have delta P over L, which is length of the pipe, is equal to 2 tau over R, right? We bring L here because we want to find out what is the pressure gradient, or pressure gradient means delta P over dP over dx, right? Or pressure drop in per meter of the pipe, or per length of the pipe. So that's why we bring that as an equation like this. Okay, what would be delta P over L? Delta P over L is pressure gradient, or dP, if the L is very small, because we know that it's a fluid element, right? Fluid element means that the L should be very small, And if you make it delta P over delta L or delta X, then you will have the pressure gradient here, okay? So it's going to connect you to dP over dx, which is the pressure gradient, and you will find out later. But 2 tau over R is going to be equal to delta P over L in that, okay? So what else we know from tau here? So we know that tau by itself is equal to minus mu du over dr, right? Again, let's come back up here. What we started, when we started this part, we found out that we are going to find u as a function of r, right? So again, by force balance, we connect these, we found the force balance with momentum equation, and we make it simpler and simpler to connect delta P, L, R, and 2 tau, okay? Then if you replace tau with minus mu du over dr here, then you will have delta P, L, 2, R, and a derivation or partial derivative of velocity versus R. Then by getting the integral, you can find out what is u or velocity here, okay? So by this connection, you will find out two equations could be extracted, okay? First, you can find out that tau by itself is equal to what? Equal to tau in R by using this equation, right? If I keep tau in one side and multiply each side by R over 2, then tau by itself is going to be 2d delta P. So d means R times 2. So I multiply that to make it, instead of d, make it R, but I can keep R for now. They will show you how we can do it. So by multiplying each side by R, then delta P times R over 2L is going to be your tau that changes by R, right? As we know that this is a parabolic shape, so absolutely the partial derivative of velocity versus y is going to be different in each R that you have, right? So it's going to change by R. That's why the tau also change by R, right? So it's not going to be constant everywhere. But if you assume that only wants to find the tau at the wall, which is the wall shear stress, or shows by tau of the wall, which is the maximum wall, and what is going to be your pressure here and force here, right? You have two type of forces here. One forces is internal forces inside the flow layers, because that's your inside of your control volume. You don't care about it because those are going to be inside of the flow, right? Inside of your control volume. We are talking about the surface forces, right? If that's the surface forces, what exactly needs to for this force balance, you only need tau that is between the first layer close to the wall and the wall, right? So you are talking about this tau for this force balance, but by itself tau here is also shows up between each layer. As long as that the flow is viscous, you will have viscous effect and you will have the tau between the layers. But when you define your control volume or fluid element like this, then whatever you have out or around of this control volume, between the control volume and surrounding area, or at the boundaries or surface of the control volume, you will need to find it out. Since we found out that it's an element, then you will have a velocity here, and you will only need the tau here. Okay, that's why we only take care of the wall shear stress when we need that. So if you want to find out the wall shear stress, what we have to do, we have to put R equal d over 2, right? Because that's tau is a function of R, and change over R with different R, as we know that here is going to be different shear stress between the layers of the flow here at the center and also at the wall, based on the derivative that we have for velocity versus R. Now, if we assume that we want to find tau wall, then we need to replace R by d over 2, right? So if we replace that by d over 2, so delta P times d over 4 L is going to be your final answer for tau wall. Okay, that's the highest shear stress in the pipe, and also that's going to be reaction of this force is going to apply your pipe. Okay, so for example, if you have a flow inside the pipe and it has a velocity and it's going to be fully developed, okay, when the flow passes over it, you need to have a external force to keep the pipe stationary. That's the flow. That's why you need the tau wall shear stress, right? That the tau wall multiplied by surrounding area is going to be the force that you have on the other direction, okay? And is the flow is the force of wall on the flow, and the reaction of that, which is in this direction, right, is going to be applied on your flow on the pipe. So you need the same flow on the same force to cancel out this force and keep your pipe stationary. Again, what you for that reason you need most of the time tau wall, and tau wall is even more important than the tau or shear stress that you have between the layers that is function of R. Okay, so perfect. If you apply minus mu du over dr here and get the integral, or multiply each side by dr and then bring minus mu here, then you have u or du equal to a term as a function of r times dr, and by getting integral you will find out what is the u or your velocity profile. So we'll do that next time here, and I wrote it that what is the final answer for that. Okay, by getting the integral you don't need to do that again, because whenever you have that equation, that's going to be for the whole pipe, right? It's going to be the same for whole x, and again u is only function of r. So you'll find that out here, that what is the velocity or u, that component of velocity in x direction, because the flow is only one dimensional and it's only in x direction, but it's not function of x. So in x it is moving in x because the component of velocity is in x direction, but it's not changing by x. That's the difference. So this u is only a function of r. Okay, you can do it by yourself, that how you can get the integral, and the only thing that you need to do is to use the delta p and tau relationship, and that the one that tau is delta p r over 2l, and the l is length of the pipe, and then replace tau with minus mu du over dr, and bring dr in one side and keep du in the one side as a single term, and get the integral. You will find out you have the same integral here, but I wrote it down here in the notes, and you will have how to get integral. So I wrote it down how do we find equation 3, which is the ur, and by getting the integral from each side. So getting integral, you need to add a c or single term here, or constant number here, because the integral gives you that. And you know the boundary condition. What is the boundary condition? Boundary condition means that at d over 2, which is your velocity at maximum, at d over 2 you will have velocity of 0, right? By applying the boundary condition like that, you will find out what is the c, and apply c, you will find out that what is ur. Okay, you can do it by yourself again and redo the work, but again this is going to be the same, and you will have it in the exam. Okay, as long as I didn't ask you that how you can develop it, but right now that's enough for now. Okay, so what's next? You will find out what is the ur, velocity profile. So what can do after that? After that, we can write what is the volume flow rate, right? Why we need volume flow rate? We need that to find the velocity average of the flow, right? As we talk about later, and also in the previous chapter, that when you have a velocity, that the velocity profile is locally changed, right? If you want to find the q, you cannot write rho a v, right? Because v is changing by each point here, right? That's say that you have to get integral of that to find out what is the mass flow rate or what is the volume flow rate, which is AV. Okay, But if you have the velocity average, then this is going to work. How we can find the velocity average? By getting the q and by getting q over a. That would be your velocity average. So first let's find out what is the q and what is the pipe volume flow rate. That how much amount of amount of volume of the flow is going, volume of the liquid going to pass in the time. Okay, so UdA is the equation, and you have to get the integral over the dA, or the differential area that you have. But again, dA you have to replace that by 2 pi r dr. So I'll consider that this is my cross section area, and I will get a very small or very thin shell here, that the thickness of that is dr. Okay, if that's dr, what would be the area? And the area of that absolutely is dA, right? The area of that is dA. So the dA is going to be the perimeter of that times dr. So 2 pi r dr. 2 pi r, that's the r, is going to be arbitrary, so it's going to be r. And if you get the integral from 0 to r to end, which is r d over 2, then which is the end of this line, and r from 0 to end, by getting the integral, then you will have the whole area, and you cover the whole area. What you are going to find out in each of these shell or thin shell is what is the volume flow rate there. So you know that the velocity in all over the area is constant, because r is constant, and you know that it's not a function of theta, right? So ur, as a specific r, that the thickness of that is dr for dA. Okay, 2 pi r dr, replacing by dA here, then and getting the integral, we will find out what is the q, right? From ur, we will replace that by this equation. Again, you can do it by yourself in home, but it's not going to change. The final answer would be pi d to the power of 4 delta p over 128 mu L. Okay, that's your q. Okay, what about V average? V average can be found out by q over a, right? So if you have pi d4 delta p over 128 mu L, and you multiply it by 1 over a, which is pi r squared, right, or pi d squared over 4, then you can have bring 4 here on top and cancel out with 128, which is 32, and 1 of d squared with the 2 of the power of that. Then finally, and also we can get rid of the pi here, right? This 2 is going to be 2 here, and 4 is going to come here, and you have 32 here, right? If finally you will have V bar, which is equal to delta P, and you have d squared here because of that, over 32 mu L. Okay, that's your final answer for V bar, whenever you have. So what till now you have it? You have equation for tau wall, right? You can find out what is the tau wall, and also you can find out what is the pressure drop all over the L, or per length of each pipe. If you have a long pipe and you have the L, then you can find out what is the absolute amount of pressure drop. Okay, and now you find out what is the velocity profile, how you can find the Q and V bar. Okay, that's all for for a fully developed laminar flow. Okay, but what is the next? Next, you can find out what is the delta P, but in general form. In general means you have inclined pipe. So when you have inclined pipe, then P1 and P2 would be there, the flow comes in, goes out, okay? But the flow by itself has a W, right? So if you remember here, we have a horizontal pipe, right? So the flow rate was in this way, which is 0, right? It, it doesn't have any effect in the x direction, and we write sigma of x only in x direction, and wf is in y direction, so we didn't care about it. But in general form means that you have that inclined pipe, that you have a theta angle here, right? If that's the theta angle, then one of the components of this force or weight force is going to be in the direction of your x that you have. Okay, so if my x is in the direction of the pipe, and that's our y, but by itself wf is in the direction of g, right? So you have one component of that comes in the direction. So how we can find it out? If that's a fluid element, and we can replace that the wf is gamma times L, okay, and times area of the C, or area, this is going to be your wf, right? But at this velocity, if that's theta, then this will be gamma LAC times the sine of theta. That's going to be the component of force in the in the direction of the flow passes over that. Okay, by getting that force, effect of that force, and applying in the equation that you had before for delta P, which was delta P over L equal to 2 pi over R, the only terms that is going to be a friction force is the force that you have at theta. So it's going to be different based on the theta. If theta is in this direction, then going to be a moving force for you in the direction that the flow passes. Okay, if it's the other direction, then going to be negative sign. But the sine of theta by itself has a sign that if theta is more than pi over 2, if it's that pi over 2, then you can say that okay, tau is 0, sine of theta is 0. Okay, the effect of that is 0. If the flow is in tau equal to theta equal to theta equal to 0 means that it's a horizontal pipe, so the effect of that going to be out, means the sine of theta is 0. If it's pi over 2, then the effect of that is higher, highest amount is gamma L, right? But if that's 3 pi over 4, right, is going to be like this. It's less than pi over 2, it is going to be negative, the sine of theta is negative. But if it has more than pi over 2, is for example 5 pi over 4, then it's going to be negative sign, and sine of theta has a negative sign and going to be positive in total and added to delta P. Okay, these are all different things, but in general the only term that is going to be the difference between the inclined pipe that is more general form versus the one that you have a horizontal one is gamma and sine of theta going to add it here. Okay, minus gamma L sine of theta is going to be added as another force when you write it down, the force balance as it shows here. Okay, so again, whatever you have as a delta P in all the terms that you have delta P there, you have to add minus gamma L sine of theta there. For example, in Q, you will find out what is the Q here. So instead of delta P, you will put delta P minus gamma L sine of theta here. Okay, so here you have velocity profile, that delta P is also part of it. So whenever you need to find out what is the velocity profile, again you need to replace delta P with that. Okay, that's all you need to do, because again velocity profile going to use this equation to find the velocity profile as we talk about the integral terms. Okay, that's why again that would be shows up there, but linearly changes, just delta P replaced by delta P minus gamma L sine of theta. Okay, if theta is 0, then you see that theta is 0 means horizontal pipe, this is going to be cancelled out and going to be 0. Then this equation for Q is going to change back to the Q that you had here, and also this one is also the same. Okay, but is it still enough for us to do that? We talk about the pipe flow by all the parameters that we needed. Still not enough. What else is needed to we'll find out. That's the friction part. So these are all based on the pipe, right? So the pipe flow by itself has a viscous effect. Okay, but it's not always like that, that the friction that we have is only because of the viscous effect. Okay, so if you have a turbulent flow, if you have a different type of or different roughness in the pipe, means rough means how much smooth is inside of your pipe wall, this is going to be different from the equation that you have. So Q in experimental shows that going to be different with theoretical answer that you have. Okay, so we need to move from this theoretical equation and give you more general equation to find out what is the friction in general. Okay, so first we think that that's only theoretical part. Okay, let's do the dimensional analysis and find out what is the friction. Okay, so first doing the dimensional analysis and write that what is the delta P, that is pressure drop inside the pipe, is related to. Okay, so we found out that delta P is related to tau, so it's absolutely related to velocity, is related to L, right? In the equation you will find out that it's related to L. It means that it relates to the length of the pipe, and also D shows up here because of the area, so it's going to be different with the different D, that is because of the Reynolds number, right? And also because of the mu, and mu is going to be inside of tau, right? These are all the terms that could affect your delta P. So we'll write it down, what is the parameters that you are going to do dimensional analysis for. So if that's your if the first listing your variables, you will have 5 variables, right? 5, which is your K, and R is going to be 3, right? LMT. Then you can say that I have 2 pi groups here, pi terms here. Okay, 2 pi terms you can be find out by this. Okay, if you do the dimension analysis that we talk about in chapter 7, and define the delta P is one of your dependent variable, and also keep L or D, one of these two out, means L is better because D is going to be your characteristic length. You keep that as a repeating variable. Then you will find out that D delta P over mu V is going to be one of your pi term. It should be equal to a function of L over D, and L over D is another non-dimensional term. Okay, if you assume that the pressure drop is linearly proportional to the pipe length, assuming means that they found it by the experiment, right? If you assume that these two are related linear means that y is ax, right? That's the equation for a linear relation between y and x. So it means that you need a constant number here to multiply by L over D and find out what is delta P. Okay, so I will change this equation, D delta P over mu V, which is equal to a constant C that we don't know what is that, right? By finding constant times L over D, then you will have a relation instead of an equation or function that phi was unknown, right? So now relate these two with linear term. But if you keep delta P in one side and rest of the terms the other side, so means that rewrite that delta P and bring L here and the rest of the terms the other side, then delta P, which is the pressure drop, again delta P over L is one of the most important things that you want to know. What is the pressure drop per length of a pipe, right? The same that we did here, also we have delta P L over L. So we keep delta P over L here, and the rest of those going to be C mu V going to go up and over D squared, right? D and D going to multiply by each other, so D squared. Okay, this is going to be your pressure drop or pressure gradient. Delta B is pressure drop, but over L is going to be your pressure gradient. Is amount of change of pressure versus the length of the pipe. Okay, that would be pressure drop per pipe length or pressure gradient. and also you have a constant C. Okay, again, these are come from experimental study. For a round pipe, the C is 32. Okay, and if that's 32, then you will know that delta P over L is going to be 32 mu V over d squared. This is your equation, additional equation for by doing the dimensional analysis. Okay, but delta P over L is not non-dimensional quantity. Okay, if you want to do it non-dimensional, again, these are all depends to the experiments and by adding more parameters there. This is not any theoretical things behind that. So I'm going to multiply each side by L and get rid of the L here, and again bring delta P in one side over 1 over 2 rho V squared, okay, which is our dynamic pressure. Why we are going to do that? Because dynamic pressure by itself is a pressure, and delta P over 1 over 2 rho V squared is going to be non-dimensionalized, okay. Then what is going to be in the other side? 32 mu V over d squared times 1 over 2 rho V squared, right? I multiply each side in that. Also bring L in top because L from here comes up, right? Bring L here and then multiply each side by 1 over 2 rho V squared, or pressure, dynamic pressure. Then finally the delta P is going to be delta P over dynamic pressure, or 1 over 2 rho V squared, is going to be equal to 64 over Reynolds. We can bring Reynolds out of it, and it's going to be 64 times mu over rho Vd, and just rewriting by just bringing some of the parameters at first, and 1d, bring 1d in here and other d in the other side, and make it two non-dimensionalized term. Then this is going to be your Reynolds number, right? Then this is going to be 64 over Reynolds. This is going to be 1 over Reynolds. 64 over Reynolds times L over D. Okay. Why we are doing that? Because we are going to put a name for it, which is here is F for friction factor. For laminar flow, this 64 over Reynolds is going to be your friction factor. Okay, it means that delta P by itself, it depends to the velocity profile. Absolutely, you can find out delta P by getting the velocity profile and also getting the tau, and in different R we can find it out what is the pressure drop. But also by knowing the Reynolds number, you have another equation for that, that delta P is related to the friction factor 64 over Reynolds and L over D. That's another equation that you can use it for finding delta P. Okay, perfect. So till now you found out what is the pressure drop. So what's the next job that we are going to do? Applying conservation of energy. Okay, you remember that we applied conservation of energy before, right? So you have a pipe that you have friction, you have tau, and you have loss of energy. That's why the pressure, if the velocity is the same on both sides and you have a pipe that is horizontal, then Z is not changing from inside to outside, and also velocity doesn't change, or velocity average, it doesn't change from inside to outside, but pressure changes, right? So if you have a streamline inside the pipe and apply Bernoulli, okay, you will find out that by Bernoulli means that these two are zero. Okay, so we at first you assume that there is not any loss in the pipe. you will find that you need the pressure difference between these two. So P2 and P1 should be different. Why? Because we want to have the flow that moves inside the pipe. So flow is from higher pressure moving to lower pressure, right? Velocity profile is the same, so we can get rid of these two terms, right, in the Bernoulli. We'll talk about alpha later, but let's say that this is velocity average, and velocity average over 2G is going to be the same, because in the pipe we found that it's a fully developed laminar flow, right? And also the Z term, if we assume that the flow is in the horizontal pipe, that again we need the same pressure difference to pass the flow over via the pipe, then also we can get rid of the Z's. So it's going to be a closure problem here, because P2 and P1 are different, but we found that these are equal with the Bernoulli. Okay, so it's going to be not true, except that you have another term which is the loss inside the pipe. What does it mean? It means that you have a higher pressure, okay, and you are coming to lower pressure, but you compensate that this difference by the amount of loss that you have inside the pipe because of the friction forces. Okay, that what is the friction forces is the viscous effect between the layers, okay, or between the layers and also the wall of the pipe. Okay, so what we are going to do here, we are going to find out how much loss each pipe has, right? So it's very important for us, because we are going to understand that the loss is going to be the amount of power that you need to compensate for that. That's all that you need to find out what is the loss. Also in the homework you will have it, the loss, and you talk about major and minor losses here, and we are going to finish it today and give you time to solve that question in the homework. But for now, let's talk about the equation of energy. Okay, conservation of energy. We have conservation of energy. We assume that the flow is steady, incompressible, so rho is going to be equal everywhere, and we don't have any shaft work. So if we don't have any shaft work, then HS is going to be 0. Okay, perfect. So keep that for now as equation 1. But what is the alpha? Alpha is the kinetic energy coefficients. So kinetic energy V1 squared over, or V2 squared over 2G, whatever is that. This term is going to be kinetic energy term, okay? And that's compensate for non-uniform velocity profile. So these are when you have V1 squared over 2, if you apply the Bernoulli or energy equation on the input output of a streamline on the streamline, or in the flow that have uniform flow over there, okay, then as long as you don't have any velocity average here. So if you have velocity average, that's going to be totally different. But when you have a different velocities here, V1 and V2, and alpha 1 and alpha 2 are the coefficient that are depends on how much your velocity profile is different with a uniform velocity profile. So if that's a uniform velocity profile, then it's going to be alpha 1 and alpha 2 going to be 1, right? So for uniform velocity, alpha is 1, right? That's why we didn't have in this alpha before in our conservation of mass and momentum that we applied, and conservation of energy after that, because we are applying that on a very small part of dA or output, because in that part you can assume that the flow is uniform, right? When you apply that on a specific element of the surface, which is the dA, then alpha is going to be 1 because the flow is uniform. Or before that, on a streamline, again you have the same assumption that alpha is 1. But now that you have a pipe, that you have a cross-section area, and the alphas and the velocity profile is different. For example, you have an in-trans region. If you are in in-trans region, if you have input that you have a uniform flow, but inside of the in-trans region you have a, or after that an output you have a parabolic velocity profile, right? So the alpha is also going to be different. even though that the velocity average could be the same, but the velocity profile is different. So you need to do compensate for that by alpha, or the kinetic energy coefficient, okay, which is alpha. But what is important here, when you are in the fully developed flow region, that we are doing this analysis on that, then alpha 1, alpha 2, v1 squared, v1, v2 squared, that our average velocity are all the same, right? Because velocity profile doesn't change. So whatever you have in the pipe for fully developed pipe flow, velocity profile does not change. Then alpha 1 is equal to alpha 2, and v1 average is equal to v2 average, and also the profile are the same. So what does it mean? It means that in terms of energy, these two are the same and it's going to be cancelled out. Okay, perfect. We don't have any hs here, also we get rid of the term. Let's rewrite the equation 1 with these two assumptions: no hs, and get rid of the term of kinetic energy terms. What we left is that HL, which is your loss, is going to be P minus P2 over gamma, bring all the terms on the one side, plus Z1 minus Z2, which is the potential energies term, okay? So that means that how much is the difference between the height inside and outside, okay? So if you have a pipe like this, okay, you can first replace this part with delta P, because P1 minus P2 is going to be delta P. And also, if your Z1, if you put your Z equal to 0 at Z1, then Z2 is going to be L sine of theta, right? This is going to be positive. Then Z1 minus Z2 is going to be minus Z1 minus Z2. Z1 minus Z2 is going to be 0 minus L sine of theta, right? Then delta Z that you have in the loss function is going to be minus L sine of theta. By replacing this delta P here and minus L sine of theta, then you can write it down that HL, which is your loss, is equal to delta P over gamma minus L sine of theta. What is that? Is the head loss in a pipe in laminar flow and fully derived. Remember that what is the assumption? It was from first, okay? But for the general analysis, we found out what is that, right? Again, you can replace delta P with the equation that you found out before, between the tau relation between tau and delta P. Remember that we have delta P over L 2 tau over R, and then we make it general with the inclined pipe, which is delta P minus gamma L sine of theta over L is equal to 2 tau over R. If you replace that, means that multiply E psi by gamma, and then multiply E psi by gamma, and also bring this term, means that bring one gamma out and bring L on the other side, then you will have delta P over gamma minus L sine of theta. You make this term to replace it by what? HL. Why? Because delta P over gamma minus L sine of theta are going to be HL, right? Then this term, which is HL, is going to be here, which is again HL, is equal to 2 tau L over gamma R. So finally you have another equation for HL, which is 2L tau wall, because you can replace that tau with tau wall by getting D at R. So gamma D. This is equation for the loss in a pipe when you have this term HL and replace tau with tau wall and R with D over 2, right? So if you have D over 2, then you can apply that, or D, and you can have that as HL. Okay, that's another equation that you can put there. And you have the loss inside the pipe. So we have to stop here by today. Next class I'm talking about the fully turbulent pipe flow, and also I'm trying to solve 2 or 3 questions at least for you that helps you to solve the homework. Okay, so for now we found out what is the velocity profile in the pipe flow, especially talk about laminar pipe flow, the friction term, and find out what is the delta P and relation with the velocity profile and tau of the wall or wall shear stress. And also we found out how we applied the conservation of energy inside the pipe, and we find out what is the delta the loss, head loss inside the pipe. Okay, so for now that's enough. We'll talk about it later and solve 2 or 3 questions and apply the conservation of energy in the laminar flow. Have a good one.